All right, here's 6-7, normal as approximation to binomial. Note that this is a normal as an approximation to binomial, okay? So why using the normal as approximation to binomial can be useful? Well, when we use the normal distribution, which is a continuous probability distribution, as an approximation to the binomial, which is a discrete distribution, a continuity correction is made, okay? So if you want to do this kind of thing, you have to use this continuity correction. So that is, if you're looking for the whole number x, you have to do the range of values between x minus 0.5 and x plus 0.5. So that's kind of the continuity correction that we might do. Key concepts for using normal distribution with approximation to the binomial. We need to have a couple of requirements satisfied. Basically, the number of successes is greater than or equal to 5, and the number of failures is greater than or equal to 5, okay? The mean, mu, is greater than or equal to n times p, and the standard deviation, sigma, is greater than or equal to the square root of n times p times q. So just to review, guys, right, binomial probability distribution, fixed number of trials, trials must be independent, each trial must be classified as one of two outcomes. The probability of success remains the same in all trials. When we solved the binomial probability formula before, and I recommended using technology because once you understand the formula, the technology will be the better way of doing it because it's more efficient. And you can refer to other videos for that. Approximation of a binomial distribution with a normal distribution, n times p, yep, greater than or equal to 5, n times q, greater than or equal to 5, yep. And we need these to be satisfied. So procedures, verify that that's true, find the values of the parameters, identify the discrete whole number x that is relevant to it, draw a normal distribution centered about mu. Oh, sorry, that should be over here. Then draw a vertical strip area centered over x, mark the left side of the strip with the number equal to x minus 0.5 and one to the right of that as well. And consider the entire area, the entire strip to represent the probability of the discrete whole number itself. Again, keep in mind, this is for basically if we want to use the normal as an approximation to the binomial. Generally speaking, right, if you have a binomial distribution, you can just calculate on your calculator. 5, determine whether the value of x itself is included in the probability. Determine whether you want the probability of at least x, at most x, more than x, fewer than x. The one reason why I'd like to talk about this too is there's a really good visual to understand at least, at most, more than, fewer. Some of you guys, I think, get tangled up on those words. But again, try to make them simple. Think in simple examples like, did you get at least 2 right on a quiz out of 10? You're like, I got 3. So you got at least 2, right? Yeah. So, 6, using that, find the x, find the area of the shaded region, find the z-score, use the z-score to find the area to the left, and adjusted value. So, for example, if you find the probability of at least 122 men among 213 passengers, you actually go to 121.5, at least, meaning that and greater, right? So that's that blue area that's shaded. If you want to find exactly 122, it would be this interval between 121.5 and 122.5. Already said this slide, but just as a reminder. And then at least 8 means 7.5 and greater. This is, again, if you're going to use the normal as an approximation to the binomial, right? Continuous or discrete, okay? All right, different things. More than 8, right? 8.5 or greater, right? At most 8, so up to 8, including 8. And fewer than 8, right? So fewer than 8 would mean less than 8, or basically 7.5 or below. And again, this is for a normal as an approximation to binomial. And exactly, you'd be using that exact value. Basically recapping this section, approximate a binomial distribution with a normal distribution, procedures for using a normal distribution to approximate a binomial, and then continuity corrections. That's bottom line. If you have questions, let me know. But again, this is kind of a rare case. Somebody might say, hey, under this assumption, we might be assuming we can use a normal as an approximation to binomial. Light should go off, then you should know you should use that one, right? But otherwise, use the other things that we've referenced before.